Friends, in continuation of our earlier lectures on dynamic programming, we'll be seeing one more problem, particularly to understand the continuous state dynamic programming problem. The problem which we will be seeing can be solved by other technique, rather some of the techniques will be more efficient to solve that problem. The intention is not finding the solution to that problem, but it is to understand the philosophy of dynamic programming in better way. So the problem is maximize z equal to 2x1 square plus 2x2 plus 4x3 minus x3 square, subject to 2x1 plus x2 plus x3 less than equal to 4. Now, as we have understood so far, that the problem is to be first decomposed, and that's how we'll be getting the problem into multiple stages. So here in this case, we will be having our first stage as maximize z equal to 2x1 square. In first stage, we'll be taking the terms related to variable x1 only, right? So for first stage is for variable x1, and the objective is maximize z equal to 2x1 square subject to 2x1 now less than equal to b1. As you see here, we'll not be taking constant here. In place of 4 we are taking b1, and that we are calling as a state variable, right? The dynamic programming philosophy wants that the constraint limit should be converted to variable, which is called as state variable, right? So our first stage is containing variable x1. The problem becomes maximize z equal to 2x1 square subject to 2x1 less than equal to b1, right? So state variable we have got, and now for getting alternatives, okay, variable for alternative, what we will be doing, will be considering x1 equal to u1, and u1 we are calling as alternative variable which indicates alternative to u, right? Now, for making you understand the things in better way, you recall the tabular approach in which you have the alternative written in this row, states written in this column, right? States in this column is indicated by b1. In this column there will be different values of the state, and in this row there will be different values which will be indicating to you various alternatives. And in this part of the body of dynamic programming, you will be having the return function, which is a function of b1 and u1, right? Depending upon various values of b1 and various values of u1, you will be having different values of the return function, right? And lastly, we'll be finding the optimal return based upon the type of your objective function. Suppose say it is maximized, you will be finding the maximum value in each of the row, and that will be the optimal return corresponding to this state b1. Okay, so optimal return is the function of state variable, and the return is function of b1 and u1. This you have already understood through my earlier lectures. So alternative is x1 is equal to u1. We will be taking various values of x1, and that we are calling as alternative. Return function f1 as a function of b1 and u1. Now we will be putting x1 equal to u1 in the objective function, to which we call as return function also. So it will become 2u1 square. Return function's value will be 2u1 square. Depending upon values of u1, you will be getting different values of return function. Suppose say this is 0, then return function will be 0, this is 1, then it will be 2, this is 2, then it will be 2 to the power 2, 4 into 2, 8. Likewise, it will go for certain value of state, right? Now, we will be getting the best return. As we look at the problem, we see that we go on taking various values of x1 in form of u1, and we see here that as the value of x1 goes on increasing, value of return function, objective function, goes on increasing because it is 2u1 square. Now the question is, how long can the value of x1 be increased? How much value of alternative variable we can take? How much value of u1 we can take? Now we know that x1 is u1, so 2u1 is less than equal to b1. So the limiting value of u1 will be b1 by 2, right? 2u1 is less than b1. More the value of u1, more will be the value of objective function, right? But the value of u1 is limited by this constant, that is 2u1 is less than equal to b1. That means u1 will be equal to b1 by 2. So best return is obtained at u1 is equal to b1 by 2, right? And if I put that b1 that value of u1 as b1 by 2 in this return function, I will be getting the best return as 2 into u1 square, means b1 square by 4, that will be b1 square by 2. So soon I get the optimal return, my stage computations for that particular stage are over. Now we will be going on to the next stage, stage 2, right? So in stage 2, we will be considering now x2 along with x1. So the problem in stage 2 will become 2x1, maximize z equal to 2x2 plus 2x1 square, subject to x2 plus 2x1 less than equal to b2. Alright, here it is, right? For variable x2 along with x1, my stage 2 is, problem is maximize z equal to 2x2 plus 2x1 square. x2 I am taking first. Okay, why I am taking first? So as to make you convinced that this component of the problem we have already seen, and this is the new part which is coming in. That's why this method is called as multi-stage sequential optimization. We go on taking one variable, one new thing which varies in each of the stage, and the other thing we have already considered in previous stage. So b2 is the state variable, and soon I have a state variable. I should look for what will be the variable for alternative, and alternative in this case is to be taken for variable x2. Okay, so let x2 be u2, right? And soon I take u2 for x2, what remains for previous stage. Okay, for x2 I have taken u2, so this is my previous stage. Okay, for previous stage what remains is b2 minus u2. Okay, I am not saying what remains for x1. That is not proper to be used in the language of dynamic programming, because in dynamic programming we talk in terms of stages. Okay, in terms of state. So I need to talk about what remains for previous stage when I have for this stage u2 variable. For this stage I have alternative for this stage, I am using as u2. So what remains for previous stage is b2 minus u2. Remaining value of state for previous stage is b2 minus u2. Alright. Then optimal return for remaining value of state for previous stage. Now how to find the optimal return from previous stage? That is already known to us from previous stage itself. So for the remaining value of state for previous state, that is b2 minus u2, optimal return for remaining value of state for previous stage. That means I am interested in finding F1 optimal. Star indicates optimal. F1 optimal in bracket B2 minus U2. For this optimal return from previous stage F1 star, right? Now we already know from my previous stage, that is here, for F1 star B1 I get optimal return in form B1 square, that is this argument square divided by 2. So soon I change my argument or parameter to B2 minus U2, the optimal return will come as B2 minus U2 square by 2. Right? This is the optimal return for remaining value of stage from previous stage. Now, what is the return for this stage? Okay, for this stage I have taken x2 equal to u2. So in the objective function I will be substituting u2 in the place of x2. So 2u2 will be the first component and second component will be the optimal return from previous stage for remaining value of state. So here it goes. So return function f2u2 for b2 and u2 for the combination of state and alternative, it is 2u2 plus optimal return from previous stage. Okay, that is b2 minus u2 square by 2. Right? Now I will have to find out optimal return for this stage, that is f2 star b2. For that, what I may have to do normally, based on something which we have done in previous problem, we have differentiated. Normally when I want to find the maximum value of f2, I want to find out the value of u2 for maximizing f2. What normally will come to my mind will be to differentiate f2 with respect to u2. But that's not all the time way. Maybe at times this may not work. But for time being, what we will be doing, we'll be differentiating f2 with respect to u2. Because I want to find out that value of alternative for which f2 turns out to be maximum. Because my objective is maximize. Okay. So let's see what happens. Optimal return f2 star as a function of b2 will be maximum of 2u2 plus b2 minus u2 square by 2. Right? For finding u2 to get maximum of f2, that is the return function as a function of b2, I will be differentiating f2 with respect to u2. So here this differentiates to 2 and this term differentiates to 2 into b2 minus u2 by 2 into differentiation of b2 minus u2, that will come minus 1, and therefore it comes 2 minus in bracket b2 minus u2. I will be equating this to 0 to get the value of u2 for which f2 will be maximum. So what do I get? I get u2 is equal to b2 minus 2. But now my question now is whether this value of u2 gives minimum or maximum. Because when you differentiate, there is always the trouble. You get the value and then you have to check whether at that value you get the maximum or minimum. So for this we need to get second differential of f2 b2. And if that differential comes positive, there exists minimum, and if the differentiation comes negative, there exists at that point you get maximum. So let us check. We will differentiate this once again. Okay. So d2 f2 by du2 square, what that comes? This will differentiate to 0, and this differentiates to minus this again to 0, right? Minus into minus u2 plus u2 differentiates to 1. So d2 f2 by du2 square, that is the second differential comes plus 1. positive. That means the value of u2 which you get b2 minus 2 will be always giving you the the minimum value of this function, whereas we want the value of u2 which will be giving you maximum value of this function, right? So, after differentiation, you have got u2 is equal to b2 minus 2, which gives you minimum function value. And you are not getting another value of u2, where probably you would have got maximum value. When you do not get another value, that is, in such case, minimum lies at extremities. And what are extremities here? Extremity means u2 will be either equal to 0. I have forgotten to mention in this problem that all the variables are greater than equal to 0. Alright, so u2's one extreme will be 0 and another extreme u2 can maximum go up to b2. Okay, u2 can maximum go up to b2, right? Otherwise it will become u2 can maximum go up to b2. You can check this argument with the problem itself. So range extremities of u2 will be one extreme. On the left hand side will be u2 equal to 0. On the right hand side it will be u2 is equal to b2. So what we will be doing at u2 is equal to 0, when in this function if I put u2 is equal to 0, I'll be getting the best value of the return at u2 is equal to 0. At one extreme I'll be getting it as b2, this is 0, b2 minus u2, u2 is again 0, b2 square by 2. And at another extreme where u2 is equal to b2, u2 is equal to b2 means this becomes 0 and this is b2. So you will be getting maximum at 2 into b2. Now hold the ratio here we are having little diversion from dynamic programming philosophy. We are now engrossed into a problem of finding that alternative which gets us the maximum return. We were disappointed by the value of u2 which was obtained by differentiating this function with respect to u2. Why disappointed? Because this value, at this value of u2 I get minimum, whereas I want the value of u2 which will be giving me the maximum, right? Then I was required to test both the extremes, because I suspect now the function value will be maximum either at the left extreme or right extreme. So left extreme is u2 is equal to 0 and right is u2 is equal to b2. At both the extreme I have found function values. Now your problem doesn't end here. You will have to check which of these two which of these two values is better value, more value. For that, question now is which of these two is higher. As we see, that depends on the value of b2. Okay, because at 0 you are getting the function value b2 square by 2, and at b2 you are getting it to b2. So it really depends on value of b2, right? So we will be considering, we will be hypothesizing that b2 square by 2 is greater than twice b2, right? We are assuming, okay? So we are trying to solve this b2 square minus this 2 I am multiplying to this 2 b2 and I am taking it to this side. So b2 square minus 4 b2 is greater than equal to 0, right? That means b2 square is greater than or I will be taking b2 common, and I am having here b2 common, then b2 minus 4 in bracket is greater than equal to 0. So that gives me two value, b2 is equal to 0. Okay, at b2 is equal to 0, this is condition is satisfied, but that is not of much use to me. I am getting another value b2 minus 4 is equal to 0, means that b2 should be greater than equal to 4 for this to be higher. Okay, b2 should be greater than equal to 4 or greater than 4 for this to be higher than this. Okay, if b2 is less than equal to 4, this is higher, and if b2 is greater than equal to 4 or greater than 4, then this is higher, right? So this implies that b2 square by 2 is greater than twice b2 only after b2 is greater than equal to 4. Okay, so by putting so optimal return f2 star b2, you will be 2b2 for b2 less than equal to 4, and if b2 is greater than 4, then b2 square by 2 is greater. Okay, as I said that it depends on the value of b2. If b2 is greater than 4, b2 square by 2 is higher. If b2 is less than 4, 2b2 is higher. Okay, now when we look at our problem, our constraint has the right hand side less than equal to 4. So our problem limits ourselves to consider any state less than equal to 4. So in our case, the optimal return will be given by 2b2. But has it been less than equal to 5 or 6, then you probably were required to consider both the options, because one option is suppose say if it is less than equal to 6, then both the scenarios are to be taken care when you consider the constraint less than equal to 6 in the original problem. So less than equal to 6 means less than equal to 4 and greater than equal to 4 also. So you will have to consider both, but our problem has the right hand side of the constraint less than equal to 4, so we will be more zooming to this side. All right, now going to stage 3. Okay, every stage, rather previous stage, also ended up by giving you the optimal return for that particular stage, right? And it has required us to take a different path to find out the optimal return. So it will be more of a aptitude part than the dynamic programming part, right? Stage 3. Now in stage 3, you will be considering variable x3 along with x2 and x1. So your problem goes like maximize z equal to 4x3, as I have said to you. So the welcome variable, new variable which you are introducing in your stage, should be written first, and then the previous stage variable, and then the previous stage variable. That should be your style. All right. So your problem will be written as maximize z equal to 4x3 minus x3 square. This is the new entry in the objective function, plus 2x2 plus 2x1 square. This already has been considered in second stage, and the constraint is x3 plus x2 plus 2x1 less than equal to b3. So this part, 2x2 plus 2x1 less than equal to b3, has been considered. So this is just follow the arrow the way I am moving it. This is the problem which has been taken care in the previous stage. Okay, and this is the new problem. So return for this new will be handled by um, new suggestions by the objective function, and written for this problem, this component of the problem will be handled in a way it was given to you by previous stage, right? So now b3 is the state variable. You will now be needing alt variable for indicating the alternative. So let x3 be u3. Okay, u3 will be substituted by various values. So let x3 be u3. Now remaining value of state for previous stage, because x3 is ut, so this is the previous stage, so value of state remaining for previous stage will be b3 minus u3. Okay, x2 x1 combine, value which is available, which is remaining, will be b3 minus u3, right? So remaining value of state for previous stage, mm, for previous stage, it should be previous stage. I don't make a change here right now. You understand, in place of this small t you write g, previous stage b3 minus u3, right? Now the optimal return for remaining value of state from previous stage, we know that if your state is less than equal to 4, then it is twice of the argument value, parameter value. Okay, like it was f2 star of b2 was twice b2 for b2 less than equal to 4. In our case, the state value we know to be less than equal to 4. So the optimal return for remaining value of state from previous stage is f2 star. F2 star, this is third stage and previous stage is 2. So f2 star for optimal. Okay, so optimal return for previous stage, okay, for remaining value of state, that is b3 minus u3, and here is how we write it. Okay, I forgot to write it. It should be written as 2 into b3 minus u3, and as x3 is u3, I simply have to put here 4 u3 minus u3 square plus f2 of b3 minus u3. That is, see how I am writing it, 4 u3 minus u3 square plus twice of b3 minus u3 for b3 less than equal to 4, and in fact for us b3 or all state variables are less than equal to 4. Okay, and say in case it happens to be greater than equal to 4, then it will be 4 u3 minus u3 square plus, if you recall back from previous slide, right? Or you can take the slides backward and see that if b3 is greater than equal to 4, then the optimal return is obtained by b3 minus u3 square by 2. All right, but in our case b3 is less than equal to 4 is the limiting state of our problem. So optimal return, that is f3 star b3. So what we will be doing, because we are used to differentiate, so we will be using the differentiation approach. We will be differentiating f3 with respect to u3. So I will be taking you back again and see, if I differentiate this, so it will be 4 minus 2 u3 minus 2 u3. 4 minus 4 minus u3 minus 2. Okay, minus 2 it will come. Okay, 4 minus 2 u3 minus 2 it will come, right? So here it is, 4 minus 2 u3 minus 2 is equal to 0. That means u3, that in turn was the value for x3. It was the alternative value for x3, and I am getting it u3 is equal to 1. Now again, once again, the question will be there to me, whether at this point I get the minimum or maximum. So for that I will be differentiating this once again, and 4 minus 2 differentiates to 0, and minus 2 u3 differentiates to minus 2, and as that value is negative, second differential is negative, I get maximum value at u3 equal to 1. It's not compulsory that you should be using the differentiation approach for finding the best value of u3. You may use any other value, any other approach by which you will be able to find the best value of u3 for which you get the function value maximum. It could be any digital approach. But here I am finding that it is possible for me to conveniently differentiate equal to 0 to get the value of u3. All right. So now the value of u3 which remains for value of u3 which remains for, just a minute, just to hold here. Just hold. Now here, as we are seeing that the right hand side of the constraint given in original problem was less than equal to 4. So, and we understand that as the value of state goes on increasing from 0, the return also goes on increasing, and that obviously it will best return will be available to me at b3 equal to 4, right? So I am taking b3 equal to 4. Had I known that best return is available or best return can be obtained at some other value, I would be taking that value of state for further consideration, right? Remaining value, now that I have utilized out of this 4 one value for x3, one value 1 for this stage. So value which remains for me, the remaining value of state to be used for previous stage, this is b3 minus u3, that is 4 minus 1, that is 3. Okay, this will be b2 for previous stage. Now we know that b2 u2 is equal to b2, right? We have, if you go back to your second stage computation, we know from there that u2 is equal to b2 and u2 is also equal to x2. b2 we know equal to 3, so therefore x2 is equal to 3, right? Now once again, now that out of this 3, which was the value for state variable value for previous stage, right? 3, out of that 3 I have utilized complete 3 for x2. So value of state remaining value of state will be this b2 is 3. For u2 or for u2 or x2 I have utilized 3. So 3 minus 3 is equal to 0. So this is the state variable value for even previous state, that is first stage. From third I am going to second, from second to I am going to first one. So value of state variable, limiting value for state variable in first stage is 0. Now that you know b1, you know the approach of computing u1 from b1 that is available there in first stage here. u1 is equal to b1 by 2 there, and I know b1 is equal to 0, so u1 will be equal to 0. And in first stage I also know that u1 is equal to x1 and therefore x1 is equal to 0. And lastly I get the solution x1 equal to 0, x2 equal to 3 and x3 equal to 1 and f equal to 9. Okay, it really took us little longer to get us the solution, that is x1 equal to 0, x2 equal to 3 and x3 equal to 1. There is another approach in classical mathematics in which you can very easily find the solution to this problem, and that is Kuhn-Tucker condition. Okay, specifically meant for handling the nonlinear programming problem. Purpose is not solving this problem only. Purpose is making you understand the philosophy of dynamic programming, so that any new problem or any natural problem you come across, you should be able to think in a way of decomposing the problem into various stages, then finding out the states, finding out remaining value of state, finding out the alternatives, and finding out the return for the combination of the alternative and the state, and finding out the optimal return. If you are able to do this much exercise with any problem, you can very comfortably use dynamic programming. One note for use of dynamic programming in such problem, the problem should be decomposable. Okay, then only you can make the use of dynamic programming. Suppose in this problem, you would have had in this problem it was possible for you to separate variables, like in first stage you had x1 only, in second stage you had x2. Okay, only it was separatable become, and in third stage you could separate x3 only, but all the time your problems are not in of that type. You may have x1 mixed with x2, x2 mixed with x3, and sometimes x1, x2, x3 all present in one term. In that case, it becomes very difficult to make the use of dynamic programming. I don't say that it will be not, it will be impossible. It depends upon how convenient it is for you to decompose the problem. So I hope by taking out the real spirit of dynamic programming, you will try the philosophy of dynamic programming to solve the problems around you, right? So if you have any problem, you can put those problem in the comment section, or I will be happy to answer your queries. Thank you so much.